our questions now look at finding the volume by taking, again, a slice of the volume, but our slice here will give us a different type of uh, circular disc, and one with a hole in it. So we're going to get what we call an annulus, and then we're going to find the volume of that. So the curve we got here firstly is x squared, and we're going to rotate it around the line y is equal to 1. So this is where it's going to be giving us this idea of getting an annulus disc here. So the area we want is between x is equal to 0, x is equal to 1, and the x-axis. So the area in this part here gets rotated around. So what does that give us? Well, we're going to have basically the volume that's created by the cylinder minus the area that's created by the curve x squared being rotated around the line x is equal to 1. And it only happens because we're rotating around x equals 1. Do the same area around the x-axis and it's not a problem. It's just a normal circular disc. So again, our problem state is in realizing when we're going to take our integration, what our function's going to be, and that comes about because we want the volume and we want to get our cross-sectional area to start off with. So we see first that our function's we've got a change in the value of x. So our values of x are changing here. So we take a point on the curve. So, and that would be xy. We need to find two things. We need to find our radius of our curve there, and also our radius of the small circle and the radius of the large circle. So to get our radius of our circle here, we've got the line y is equal to 1. So distance of 1 there. So the large radius of our circle would be 1. Now if this is going to be the distance y here, then the radius of the small circle is going to give us 1 minus y, because it would be a total of 1. Take away the distance y would leave us that distance there. So that's where our cross-sectional area comes in. So 1 minus y, which can be written, because it's y is equal to x squared, we can put it as 1 minus x squared. And we're going to get it in terms of x squared because we're going to have delta x as our thickness there. So we want our function in terms of x. So what does that mean for us? We're able to put the difference between 1 squared and 1 minus x x squared all squared. So expanding that out, it's going to give us 2x squared minus x to the power of 4. So when we put it in with the volume, pi times that for our volume times the delta x, and it's going to be between 0 and 1. So we do our integration, we go through and we get our value of 7 pi and 15. So again, the key is to get the correct cross-sectional area. Everything else seems to fall into place. This time we've got y is equal to x cubed and y is equal to x, and the area between the two curves is rotated around the line y is equal to 1. So again, this time we have a situation where we want to we're going to get a circular disc, but it's going to have a hole in it, so it gives us the annulus there. So again, the key, we know it's delta x because it's rotating around the line y is equal to 1. So our change in our thickness of our disc is perpendicular to the axis of rotation. So this time, if we take a point and go across x there, we're going to get two different points, and we're going to have to manipulate that to get our radii of our circle. So if it's the point x there, that would be the point x cubed. I'm not going to put it in terms of y, because I'm not going to say that's xy and that's xy as well. They've both got the same x coordinate, but to get the radii of both there, we need to consider if it's both x there, that would be xx, because it's on the line y is equal to x, and x cubed was y, that point there is on the line y is equal to x cubed. So the distance there is x cubed, the distance there is x, and we're going to take it both away from 1. So that would be 1 minus x, 1 minus x cubed, and 1 minus x as our radii of our circle. So that's the values that y is going to take for our circle. And there they are there. And so the area formula, the pi times the large radius squared minus the small radius squared, and volume formula then would be times pi, delta x. So what does that look for in our volume? So expand it all out, collect our terms. We get from 0 to 1, and pi can stay out the front. Integrate those terms. Again, the integration's not hard. It's just going through and getting the correct fractions and making sure we get our correct answer. So that's where we start to look at. We get a lot of these ones starting to get an annulus, and we've got to make sure we get our radii correct for our annulus. And once we get that, everything else starts to fall in place, because it's really not that hard to get the integration of those functions in those cases.